Welcome to The Explainer. Today, we're diving deep into the world of fuel cells. We're going to look at a tiny, tiny component that has a huge job, keeping things perfectly hydrated. Now, this is a super delicate balancing act, and we're about to find out why getting it right is so critical for the future of clean energy.
So, here's our game plan. First, we'll unpack the core problem. Then, we'll look at the seriously clever solution engineers came up with. After that, we'll see how they're using modern tools to make that solution even better. And finally, we'll connect all these little details to the big picture, the future of clean energy.
All right, let's jump right in with what we're calling the Goldilocks problem. And it's exactly what it sounds like. For a fuel cell to work, everything inside has to be, well, just right. Especially when it comes to water. Not too wet and definitely not too dry.
See, right at the heart of the fuel cell is this special membrane, and it is incredibly picky about water. If it dries out, the electrical resistance just skyrockets, performance tanks, and you can even physically damage the membrane. But if it gets too wet, you've got the opposite problem. It floods, blocking oxygen from getting where it needs to go, and pretty much suffocates the whole reaction.
And this isn't just some minor inconvenience. As this quote makes really clear, if you get the hydration wrong, you're looking at what they call high ohmic losses. That's just a fancy term for electrical resistance, and you could cause permanent, irreversible damage. So yeah, the stakes for getting this water balance right are incredibly high.
So, how on earth do you solve a problem that tricky? Well, engineers came up with a really elegant solution. It's called the membrane humidifier. Let's take a look at how this little device pulls it off.
The basic idea here is actually pretty simple, but it's also brilliant. The humidifier uses a special membrane that keeps a stream of wet gas separate from a stream of dry gas. The magic is that this membrane only lets water vapor pass through from the wet side to the dry side, so it perfectly humidifies the air right before it goes into the fuel cell.
And this is where it gets really smart. The whole system is completely self-sufficient. It actually takes the hot, wet exhaust gas coming out of the fuel cell and uses it to humidify the cool, dry air going in. It's this beautiful, self-sustaining loop that makes the entire process incredibly efficient.
Okay, so the concept is solid, but how do you take a good design and make it perfect without building and testing 1,000 different versions? This is where modern engineering and a little bit of digital magic come into play.
So before they build anything physical, researchers create this incredibly sophisticated computer model, basically a digital twin of the humidifier. But you can't just trust a model right out of the box. The first, most crucial step is to validate it, to check its predictions against real-world experimental data to make sure it's accurate. Once that digital twin is validated, engineers can basically play in a virtual sandbox. They can tweak all sorts of things, the thickness of a material, the size of a channel, and instantly see how it impacts performance, all without ever leaving their computer.
So after running all those simulations and crunching all the numbers, the model pointed to 3 specific design choices that had the absolute biggest impact on how well this humidifier works.
The first key factor they looked at was the thickness of that special water transfer membrane. So, is thinner really better?
Oh, absolutely. The model was crystal clear on this. A thinner membrane lets water vapor move across much more quickly and efficiently. Now, of course, there's a trade-off. It still has to be durable enough to last for years. But the goal is definitely to make it as thin as reliably possible.
Next up on the list, the total surface area of the membrane. In this case, does size matter? Is bigger actually better?
And the answer here is a huge yes. A larger surface area just gives you more real estate for that heat and water transfer to happen. It directly boosts how effective the humidifier is. Simple as that. All right, the final piece of this puzzle is the size of the tiny channels that the gases flow through. What did the model have to say about this? And here's where it gets a little counterintuitive. You might think bigger channels, more flow, that's got to be better, right? But the model showed the exact opposite is true. Smaller channels actually create more efficient conditions for that heat and water transfer to happen.
Okay, we have just been deep in the weeds on some very specific engineering details about one small component. So now it's time to zoom out and ask, why does any of this actually matter?
So, to quickly recap, the model gave us a really clear recipe for the perfect humidifier. You want the thinnest, most durable membrane you can get, the largest possible surface area, and the smallest channels for the gas to flow through. And here it is. This is the big takeaway. The road to making fuel cells a mainstream clean energy solution is paved with thousands of small improvements, just like this one.
A tiny efficiency gain in one little humidifier might not sound like a revolution, but when you add up all those tiny gains across all the components, that's what leads to a longer driving range for a fuel cell car, or lower costs for a power plant. These small wins are what create the big breakthroughs.
This intense, almost obsessive focus on perfecting every single detail is what's pushing this technology forward every day. And it really leaves you with a fascinating question to think about. As engineers get closer and closer to perfecting all these little pieces, where is the next truly giant leap for fuel cells going to come from?